Last time, let's just remind all of us, we proved that the radius of any circle is positive. Right? That was a fun little proof we did. And then for your homework, you worked on the fact that that means that the center of a circle is always in the inside. Yes? Now let's prove an even better. So we'll come back to the proof of this. Let's prove an even better theorem. We can prove whatever we want. Whatever we want. For example, we can prove that 1 is equal to 2. Rodrigo? That's the right question. Oops. Ex falso, yeah. Of course, this has nothing to do with 1 and 2. It's that, thank you. It's that we have a contradiction in our system. And I want us to find it. I lulled you into a sense of security that we were making really good progress with being very, very clear and explicit about all of our axioms. We're being like really careful, and we were so careful that we let slip a contradiction, which means we can prove anything without ex falso. Where's the contradiction? So you got an idea? It's somewhere on this page. It's somewhere here. Rita, you see anything? It's very subtle. It's so subtle, it's hard to see. And once you see it, you can't unsee it. Just like the gaps, the gap in Euclid, we've let a gap slip. Leo, you got something?
A and B don't have to be distinct points in point of a circuit.
Point on circ if and only if. It's not here. It's related to this. Sandri and then Jivan?
I was gonna say the last thing below point, yeah.
The last thing, remember this points of circ, we added at the end because we want to have two distinct points on a circle so that we can find the center. Otherwise, if we don't have two distinct points, there's no way to find the center. And having those two distinct points forced the radii to be positive, the radius of any circle to be positive, Jivan.
It's on source here. If they intersect, it could be just one point with their tangent. So they don't have to.
No, we decided to just pretend that wasn't a thing for now, though, right?
Well, sorry, this is there was like circs if and only if we had another version of this that we decided to throw away. That was like not a good.
Oh, wait, yeah.
That was only a one-directional version.
Yeah, but if this has A is not equal to B, but that's not necessarily true. Because A could equal B.
Well, so points of circ guarantee that the radii are strictly positive.
Yeah.
This says that if the circles do intersect if and only if A is on the circle, A is inside the circle, B is on the circle, B is inside the circle, and A is not equal to B.
If it would be that means they said intersect, but only at one point.
We are not allowing circles that have only one point in.
No, like two circles intersecting.
Two circles, so it's up to us to determine what the predicate circles inter, wherever it was, circs inter. This has no meaning. We give it meaning, and we decided that we're not going to have degenerate situations like tangency. We'll only have intersections with 2 points. In fact, this is already, wait a second. Well, if you could prove that for any circle, there's some other circle that intersects it, then it would have to intersect it at 2 distinct points, in which case that circle has 2 distinct points on it. So that's kind of smells like this points of circ. It's something much more fundamental. We screwed up postulate 3.
taking a look at the next part last night and I was trying to figure out what to do next and I was able to prove one part of it, but it kept asking me to prove A is not equal to B.
Yes.
And I could not figure out how to prove it because something was just like fundamentally wrong. With
That's
the
right.
code. And
That's right.
I couldn't figure out what the problem was though.
So check this out. The way we circ of points, this is postulate 3. Given any 2 points, there's a circle through them. Is anything stopping me from taking A and A? So let's prove the Riemann hypothesis. Let's prove that 1 equals 2. Okay, we start with ex falso. I'll move this theorem up here so I don't have to have it so far down. Ex falso, let me remind you, ex falso says whatever our goal is, doesn't matter what our goal is, if we can prove false, out of false we can prove anything. So if we can prove false, then we can prove whatever we want. Let's prove false. Okay, let's prove the Riemann hypothesis. We can prove anything. So first, let's get that circle, because in circle of points, our version of postulate 3. So let me report some of this. Claim we can now prove the Riemann hypothesis, or 1 equals 2. The reason is, and it's very subtle, we very subtly let slip into our axioms a contradiction. And if you have a contradiction, you can prove anything. Okay, so we're going to prove this theorem called whatever we want. And step 1 will be ex falso. Step 1, doesn't matter what we're trying to prove, we'll use ex falso to convert whatever we want to false. Okay, so now our goal after ex falso is false. How are we going to prove false? Let's construct, postulate 3 lets us construct a circle where A and A are the same, A and B are the same point. The problem is that our version of postulate 3 allows us to construct a circle with radius 0, but points of circ implies, as we proved last time, that all radii are positive. Okay. Maybe we can't prove it. Maybe we can't at the moment prove this theorem. You know why? In order to construct a circle, first I need a point. Where am I supposed to get a point out of nowhere?
I don't need it. I have everything simple.
You need to provide an input to the theorem.
If I had a point, I would have it as an input to the theorem. There's no axiom here that says points actually exist. So, which axiom guarantees that we can actually put a point on the page somewhere? It's not there. We should make one of those. We should make one of those. How about point exists or something? Or the set of points is infinite? Let's see. Points infinite. Okay, fine. Point exists. Let's start with 1 point exists. Point exists. There exists A of type point, such that true, such that whatever. Okay. There does exist a point. So let's obtain A and, well, there's no hypothesis from point exists. Is that what we called it? Okay, now we have a point. Now we can draw a circle. So let's, what is that called? Circ of points. A says that there exists a circle whose center is A and the point on the circle is A.
Okay.
Yeah, so let's obtain that circle, which we'll call alpha. We have that A is on alpha. Actually, the first thing is A is center of alpha. And then A is on alpha. We'll obtain that from this. Is everybody with me? Following along? So let's just record that. We write this together with this to get a circle alpha of radius 0. Does that make sense? Okay, and then how do we finish it? I actually need this radius pos thing before I can state this theorem. So let me move the theorem down below radius pos. Okay, here we are. What is this called? Radius pos. Radius pos says given any 2 points. So which 2 points in which circle? A and circle alpha. Is A the center of alpha? Yes, that's called A cent alpha. Is A on alpha? That's called A on alpha. Then the distance from A to A is positive. On the other hand, so let's call this dist pos or something, just to give it a name. On the other hand, we have dist 0, which is dist pos def. Oh, we have dist self. We already proved it. Okay, great. Dist self A. The distance from A to A is 0. And now I can probably, there's a theorem already that combines these things. Should we try exact question mark? Exact question mark. Give it a second. Really? You couldn't do it? You couldn't do it? All right. Let's chain this equality and this equality. All right, there's one more tactic I have to tell you about, which is called rewrite. So let's learn another tactic. This is good. New tactic called rewrite, RW. Rewrite. What this does is it just substitutes. So here I have dist AA equals 0. When I say rewrite at dist pos, it's going to look, so I'll say, I will write rewrite dist 0 at dist pos. So what this will do, let's think about what this will do. Rewrite dist 0. Dist 0 says the distance from A to A is 0. So it's going to look for the left-hand side, dist AA, in dist pos. If it finds it, it'll replace it by the right-hand side. Okay, this will look at dist pos and try to find the right-hand side of dist 0, namely dist AA. Okay, will it find it?
No.
Will it find dist AA somewhere inside dist pos? It's right there. If it finds it, if the tactic works, meaning it finds whatever the right-hand side, then it will replace it with the left-hand side.
The right side is
I'm sorry, left-hand side, thank you. My left and right is reversed from yours when I stand here. So it's going to look for the left-hand side. And if it finds it, it'll replace it by the right-hand side. Thank you. Yeah, this is your left. So it's gonna look for the left-hand side. If it finds it, it'll stick the 0 in there. Okay, let's try it. Everybody ready? Drum roll. Rewrite. Oh, you give me the drum roll. Look at what happened to this pause. Okay. Okay, now we talk. All right. This A equals 0. And that's got to be a contradiction. 0 is not strictly less than 0. So please, exact question mark. Okay. Less than self if and only false. So there's a theorem called something is less than something else if and only if false is true. It's a general theorem. So it's called less than self if and only if false. It's a general theorem. Don't worry about what it is. If we give it the real number 0, then 0 is less than 0 if and only if false is true. So if we give it 0, and which direction do we want? I guess we want the forward direction. If we could prove 0 equals 0, then we'll get false. So that's dot MP or dot 1. Dot MP is dot modus ponens, but dot 1 is the same thing. And now it's waiting for a proof that 0 is strictly less than 0. And that's exactly what this pause is. Okay, we've proved the Riemann hypothesis. Congratulations. Shall we split the million 31 ways? Okay, so this is a problem. You mean I shouldn't share it with you? That's what you mean? Okay, so that's the whole theorem. Okay, so obviously this is bad. How should we fix it? I'm going to comment out this theorem because it shouldn't exist in our theory. Comment it out the long way so it doesn't look so bad. This is another way to comment, FYI. Okay. How should we fix this, Jimmy? When we want to construct, in postulate 3, let's look back at Euclid. What does Euclid actually say? Euclid Elements. Book 1. Two distinct points. Well, he's kind of ambiguous here to describe a circle with any center and any radius, but not radius equal to 0. Okay, so we need for any points A and B, where are we here? If A does not equal B, A not equal to B, then there exists a circle having one of those points on the center and the other one. Okay, then our proof won't work. Our proof of the Riemann hypothesis. Sorry, there goes our $1 million. Okay. You see how subtle it is to set up your axiomatic system in just the right way so that it does what you want it to, but doesn't do anything stupid. How about do we need to say that A is not equal to B in line of points? If we have a pair of points, is there always a line through a pair of points? There's infinitely many lines through one point. There's nothing wrong with A and A being the same thing. That's not, as far as I can tell at the moment, a contradiction in the system. Okay? Cool. So that's going to break all kinds of things. You can see all this red building up over here. The fact that we added one more hypothesis, which is that A is not equal to B, adds a bunch of red, but it's necessary. We don't have a choice unless we want to prove vacuous things like 1 equals 2. But B, let's see how we can fix it. So that's an equilateral triangle. This is our helper lemma that the distance from a point to itself is 0. We proved that the radius is positive. Now I think we can prove that the center of a circle is Now we can prove that the center of a circle is inside the circle. Okay, so here we are. Everybody remembers where we are? Back to the proof of in circ of center. So where are we? Okay, so we fix postulate 3 to require A is not equal to B. Let's go back to the proof of this. Okay, so here we are. We've gotten this far. Now what? We know that the radius is always positive, right? The radius of a circle is always positive. That's why we proved that lemma when we were here. So what's that called? Rad pos is radius positive, radius pos or something. And you have to give me 2 points and a circle. Which 2 points? Exactly. A, B, and alpha. A, B, alpha. Come on. Okay, A, B, alpha. Do we know that A is the center? I'm looking right here. Do we know that A is the center? Yes. A cent alpha. Do we know that B is on the circle? B on alpha. Okay, and we have rad pos is nearly the thing that we want. Do we want to, how do we convert from rad pos to the goal? We can use rewrite. So rewrite works for equalities. If I have an equality, I can rewrite. You want to rewrite distance AA into the goal? Okay. Apply will work also. So let's use rewrite since we just learned that. Let's rewrite dist AA. And if you're rewriting to the goal, you don't have to say where to rewrite it. Look at what it did. It found dist AA in the goal and replaced it by 0. Now what? Exact rad pos. Okay, no goals to be solved. Guys, we're moving right along. We might even finish, once we can prove anything with a false axiom, we're getting pretty confident here. We can prove we can actually close goals. So now we know that any point of any circle is inside, if it's the center, then it's inside the circle. Okay, let's go back to proposition 1.1. We can't even get started because we took 2 points and we're trying to show that there's an equilateral triangle. We have one of 2 options. We could allow a degenerate equilateral triangle where all 3 points are the same. Or we could insist that an equilateral triangle, that to prove prop 1, you need 2 distinct points. Which do you guys prefer? Okay, 2 distinct points. So let's add the hypothesis, A not equal to B, which will say A is not equal to B. Okay, if we have 2 distinct points, then there's a circle where they form an equilateral triangle. Okay, so what do I have to, so circ of points is not enough. I've got A, I've got B, and I need one more thing. Sorry, slow me down, take me back, yeah. If you have a question, I guarantee there's like 5 other people that are
Just talking about what the exact rad pos is.
what the exact rad pos did, sorry. So let's go back to the state before that. Rad pos was the fact that this AB is strictly positive. And our goal was this AB is true. Does that make sense? Okay. So what other piece of information do we need to give to circ of points AB in order to get the circle? It's not equal to B. And now there's no problem. How about here? Yeah, I think it's going to be the other way around. It's not, now we need that B is not equal to A, which is not the same thing. Really, guys? which is not the same thing as A is not equal to B, but I think that sim will do it. And it did. Yes.
A is not equal to B dot sim, like you just say B is not equal to
Our assumption is that A is not equal to B. And what it wants is B is not equal to A. How do we prove that? Well, that's the symmetric property. Okay, does that make sense? Okay. So we got all the way to the proof of this step 3. Why do the circles intersect? We have something that tells us that circles intersect if there is a pair of points. If we know that there exists a pair of points, so when we apply this, the pair of points we said is A and B, and we have two things to prove. B is on alpha, and B is inside beta, and A is on beta, and A is inside alpha, and A is not equal to B. Oh, by the way, we would have to prove that A is not equal to B. Right? We wouldn't be able to prove that if we didn't already know that A is not equal to B. So we break this up. The first case says B is on alpha. Should I draw this picture again, or you have it in your mind? Let's draw the picture again. So let's get GeoGebra. No axes, no grid. Descartes was not born yet. I have 2 points. What's going on? It's okay?
Yeah, man.
I have those 2 points, and I'm trying to say that B is on circle alpha. B is on circle alpha. We already know that. That's called B on alpha. And now I have to do 2 things. I have to show that B is on beta and then a bunch of other stuff. B is in beta. Okay. So why is B in beta? Yes. And what is that theorem called? In circ of center. Okay, so let's just remember have in circ of, whoops, I just want the one line. I can't copy that one line. There we go. There we go. So in circ of center says, if you give me a point and you give me a circle and it's the center, then I'll prove to you that it's in the interior. What point do we want to give? B. What center? What circle? Beta. Do we know that B is the center of beta? What's that called? B center of beta. And now we have constructed exact this. Or just, yeah. So exact this. Boom. Okay. Now, constructor, again, breaking up the fact that A is on beta, which we prove because we already know A is on beta. Y is, now we have 2 more things to prove. That A is on alpha and B is not equal to A. Write down on your page what the next line of the proof is. Yes.
Didn't we already prove that B is not equal to? Because we did A is not equal to.
Yeah, yeah, we needed that proof up here, and we're gonna need it again down here. What are you gonna use for B is not equal to A? What's that? So the question is, what's the next line of code? Right now we have 2 things to prove. Our goal is something and something else. How do we? That's what I want you to. We're gonna mimic the same thing we did before. Yeah, yeah. So first constructor. Constructor gives us 2 goals. That A is in the interior. And a second goal, what's our second goal? That B is not equal to A. Okay, take 1 minute and see if you can solve both of these goals. So goal one is point in circle A alpha. Point two, let's just do the first one. Take a second and write on your page how you're gonna solve point in circle A alpha. Yeah, it's supposed to be easy.
So you're using for this one. It's just.
Yeah. What's hero? Tells us that. Really?
Okay, Navia. Navia, tell us what you did. Guys, let's listen in. Go ahead. Yep. We're going to feed it A. We're going to feed it alpha. Now it wants that A is the center of alpha. Ah. And now?
Oh, exactly.
Yeah, now we have exactly what we want. We don't have to make a separate have out of it. We could just say exact. Exact that. And the problem with the sorry is that there's no goals. One more. How do we prove that B is not equal to A, Santosh?
Yeah.
Yes, but if I just write A N E B dot sim, that's not a I need exactly right. I need a verb. Although exact isn't a verb. Exactly is an adverb. It's still not a verb. I don't know how to make it a verb.
You can do exact something. Like, I feel like you.
Like with an X-Acto knife. Yeah, you can extract something. Anyway, okay, we're almost done. We're almost done with the proof of 1.1. Guys, we're about to prove postulate 1.1. This is very exciting. The only thing is there's no longer something called point of circ inter. We changed the name. Circs inter if and only if. And now circs inter. Okay, let's try to build this up again. So have circs inter if and only if. Okay, let's just remember what that says. It says given any two circles, so the two circles are alpha and beta, they intersect if and only if something else happens. Well, we just showed that they intersect, right? So do we want the forward direction of that or the backwards direction of that if and only if? So one more time, we want to show that there does exist an A and B. That's our goal. And we know that they do intersect. That was step 3. We finally justified, so we want the forward direction. Yeah. We finally justified. So forward direction is called dot 1. Dot 1's the forward direction, and I feed it into it. This wants a proof that circles A and B intersect, alpha and beta intersect. What do I feed into it?
Step 3.
Step 3. Okay, so this is what we want step 4 to be. I'm just going to copy this and paste it down here. Paste. And what's the matter? Let's see. Is it a parenthesis issue? There exists points C and D with C on alpha. Oh, I see. I reordered these when I changed from one axiom to the other. I reordered them, I think, like this.
We know that it's one answer battle. There's interval of the correspondence.
Ah. Yeah, what happened to the ins? I see. Point. So C is on alpha and in. Okay, let's try this. I don't remember which one it is. Okay, we can look right here and find out which one it is. In fact, we can look. Good catch. We can look. Yeah. So it's point on and then point in A alpha, A beta. So that's C alpha, C beta. Then D alpha, I guess. Point is in D alpha and point on D beta, or is it the other way around? Oh God.
D is in alpha and C is on alpha. Is that what we're trying to do?
Yeah, it's gonna be on alpha in beta, on beta in alpha. That's what we needed to say. So on alpha in beta, on beta, and in alpha. Whew. Okay, now we don't need this. Okay, step 4 is done. We obtained the things we needed to obtain. Now we know that the two distances are the same. What's the problem with C? Oh, it's because these things are not called. I don't understand. Okay, we have C and D. We have C is on alpha. Then we have C is in beta. That should be the next of the next thing is called C is in beta. Then we have D is on beta, and then D is in alpha. And then C is not equal to D. Okay. So now what's the problem here? I've got point on circ if and only if BC alpha beta, B is the center, C is on beta. There is no C is on alpha.
D is on beta.
But this isn't about D. Okay. One more time. We need our picture. Step 4 says there exists circles C and D. There exist points C and D. So I'm just going to mark those points. Here's C, here's D. Oh, they're not in, they're all on. Both C and D are on. That's why they were all on. This was on. So then do we have circles inter wrong?
What I was confused about when I looked at
Ah.
last night and it's just before we had search inter and search inter was different than search inter if and only if. But we did
Yes.
because we thought we didn't need it.
But we do need it. And it's a different thing. Oh my gosh. Okay, I think I can just hit undo a whole bunch of times.
Wait, no, go.
Oh, that's true. That's a good point. Have I been doing a good job of keeping track of the version history? I don't think I have.
Yeah, points of circ center.
Points of circs inter. Oh my gosh. That would have been very bad. is about to be very bad. So you see, every time you add a new hypothesis, you have to wonder, did you introduce some kind of problem? So I got very confused because I'm looking at text instead of a picture. If we were looking at a picture, everything is clear, but it's a little too clear, right? So that's why we're gonna use text to make sure we're doing exactly the thing we need to be doing. So this is, what's it called? Points of circs inter.
And everything needs to be on.
And then these need to be on, and they need to be on in the right order. Actually, maybe we have that here. Maybe we have that here. Step 4. I'm just going to copy step 4. Here was our original step 4. We don't need to obtain this twice. And ladies and gentlemen, we have proved prop I.1.
I think that's enough on there.
Okay. I.2. Let's start I.2. Let's look at let's do it as human beings. As human beings, let's do I.2. Okay? Not as computers. Prop I.1. Let's review. Prop I.1. Let's look at it again. We want to make an equilateral triangle. We're given A and B. Now we know that A and B had better be different. Right? A and B are two different points. We constructed those two circles. We constructed their point of intersection C, which Euclid didn't justify, and we spent a whole bunch of time figuring out how to justify properly. Once we did that, proposition 2. To place a straight line equal to a given straight line with one end at a given point.
Oh, and this needs line segment.
It doesn't need line segments. You can think of it as line segments. It needs something related. Let's go over what the math of this is. Okay. Let A be the given point and BC the given line. So we're given a point A. Let me undo everything. We're given a point A, and we're given a line segment, and a line segment BC, just some random place somewhere. And my goal is to draw, let me write this down, onto proposition I.2. We're given a point A and a line segment BC. Our goal is to draw at A line segment of length BC. So now think about what you would do as a high schooler. You are high schoolers. You would take your compass. You would put your compass at B to C. You would lock the compass in place. You'd pick it up and move it over to A and set it down. And draw a circle at A with radius BC. With GeoGebra, you would take, this compass tool. The compass tool says, select the segment. I'll select that segment, and then I'll select the center, and boom, I've done it. But in Euclid, this is a theorem. His compass is collapsible. The second if you have a compass down on your page, you can turn it and make a circle. The second you lift it up off the page, you lose the distance. It does not have a locking mechanism. Okay, you understand? So Euclid's compass, let's just record this. With modern compasses, you just put the spike, what do you call that? The center, the thing that pokes in, the spike at B and the pencil at C, tighten the compass, and pick it up and move it to A. Or in GeoGebra, there's a tool. There's a tool called, what was it called? Did it have a name? It's just called compass. It's literally called compass. There's a tool called compass that lets you do this. Let's take a picture of this compass. Come on. Oh, come on. Let's take a picture of this compass. There we go. That's the compass tool. But Euclid does not allow this. He knows that his axioms do not allow this, does not allow this, does not allow this. His compass is what we call collapsible or collapsing. It only works when it's first put down on paper. So postulate 3 says, if you give me 2 points, I can draw the circle centered at that point, passing through that point. I can't go measure the 2 points somewhere else and move that radius to my given point and draw there. So here's your homework. I mean, you can cheat if you want to read how Euclid did it, or you can just think about what you would do using only Euclid's collapsing compass. In fact, we could spend a few minutes now if you want to think about it. Let's spend just a few minutes thinking about how you could possibly solve this. How are you going to move this length, this distance from B to C to the point A? Where do you go? What's that? There's no axiom of estimation.
You just use you can.
Yeah.
Okay, great question. There's a great question from Pre-Day. Why can't you just use a ruler? Question. Why can't you just use a ruler? If you notice, I've been very careful in my description of Euclidean geometry. I did not say ruler and compass. Straight edge and compass. Euclid's geometry is straight edge and compass, not ruler. You can't mark, you don't have an axiom that allows you to mark your straight edge. It's not a ruler. If you had a ruler, absolutely, you would measure it and just move your ruler over, right? There's no problem. That's not how Euclid. You can say it's a stupid rule. That's perfectly fine, but that is the rule Euclid set up for himself in this game. You know, as we're determining the rules of the game as we go along. So that's the question. Actually, we can state this formally as well. Given a point A and 2 points B and C, is there any reason the distance between B and C has to be positive? If the distance between B and C is 0, if it's just a point, then it's easy to move a point of a length 0 to A. Let's say B and C are different, okay? So two pieces of homework. Problem 1, state this formally. State proposition I.2 formally. I think you can figure out how to do it. Given 3 points A, B, C, there exists a point D, so the distance from A to D is equal to the distance from B to C. We're trying to construct a point D somewhere at distance BC from A. That's homework 1. Homework 2, this is a real homework problem. Solve this problem in natural language. In other words, not with halves and obtains and constructors, unless you want to. So star for formal solution. But first, let's find an informal solution. How do you move a length from wherever it is to the point A without a ruler, with a collapsing compass? Is that a challenge? You guys like it? I think you can do it. All right.